Imagine for a moment that you are standing at the edge of two frozen wastelands. In one hand, you hold a ticket to Antarctica, Earth's most inhospitable continent, a place of crushing cold, howling winds, and endless ice. In the other, a ticket to Mars, the red planet of dreams, the next frontier, the world that captures our collective imagination with visions of glass domes and terraformed gardens stretching beneath alien skies. Now imagine being dropped, unprepared, onto each world in turn. Which one would end your life first? The answer might surprise you. In fact, the difference is so profound, so absolute, that it challenges everything we romantically believe about humanity's future among the stars. Tonight, we drift toward a truth that hides beneath the shimmer of science fiction and billionaire ambition. We will explore not why Mars is difficult to reach, but why even after arriving, even after planting flags and building habitats, it remains orders of magnitude more hostile to human life than the harshest place on Earth. Antarctica, with all its frozen brutality, is a paradise compared to the red sands of Mars, and understanding why reveals something fundamental about what it truly means to be alive on a planet that wants to keep you that way. Mars occupies a peculiar space in human consciousness. It glows in our night sky like a promise written in rust and iron. For more than a century, it has been the canvas upon which we paint our grandest visions. Canals that never existed, civilizations that never rose, and now, colonies we have yet to build. Tech visionaries speak of million-person cities beneath Martian skies, of making life multiplanetary, of transforming a dead world into a living one through sheer force of will and engineering. It is a beautiful dream, a necessary dream perhaps, but it is a dream that floats on assumptions we rarely examine. Antarctica, by contrast, inspires no such romance. It is Earth's forgotten extreme, a continent larger than Europe, buried beneath ice up to 3 miles thick, where temperatures plunge below -130 degrees and winds scream across the polar plateau at hurricane force. Fewer than 5,000 people inhabit its research stations during summer. In winter, that number drops below 1,000. No one is born there. No one has ever called it home in any permanent sense. It remains, after more than a century of human presence, a place we visit but never truly inhabit. Yet this frozen wasteland, this corner of Earth so hostile that early explorers regularly perished, just trying to map its coastline, this is our Mars analogue. This is the place scientists point to when they want to test equipment, study isolation, and understand what it means to survive at the edge of habitability. And here is where the story becomes strange. Because if Antarctica, with all its advantages, with breathable air and accessible water, with rescue measured in hours rather than years, remains largely uninhabited, what does that tell us about Mars? The answer unfolds across a series of quiet revelations, each one subtle, each one devastating. Factors we take for granted, air pressure, atmospheric composition, radiation shielding, the simple proximity of help, become chasms of impossibility when removed. The difference between difficult and impossible is not always a matter of degree. Sometimes it is a matter of kind. Before we journey deeper into these frozen worlds, I'd like to ask something of you. Wherever you are right now, in whatever corner of Earth you call home, take a moment and leave a comment below. Tell us where you're watching from and what time it is in your world. It's a small thing, but it reminds us that we are all fellow travelers on this fragile blue sphere, contemplating together what it means to leave it behind. Now let us begin. Let us descend into the ice and dust. Let us compare the frozen reality we know against the frozen dream we chase, and discover why even Earth's most hostile environment remains a sanctuary compared to the silent deserts of Mars. We stand on the frozen plains of Antarctica, where the wind cuts like a blade and the temperature plunges to depths that would freeze flesh in minutes. Yet even here, in one of the harshest environments on Earth, we can do something extraordinary, something we rarely think about until it is taken away. We can breathe. The air is cold, yes, painfully so, but it fills our lungs with oxygen. It sustains us. It is invisible. It is often taken for granted, but it is the thread that connects us to life itself. On Mars, that thread does not exist. The atmosphere of Mars is not merely thin, it is almost an absence. Where Earth's atmosphere wraps around us like a protective ocean of gases, Mars offers only a whisper, a trace so faint that stepping onto its surface would be, in atmospheric terms, like stepping into the void of space itself. The composition is hostile, 95% carbon dioxide, a gas that would suffocate us within moments. Only 0.13% oxygen, not nearly enough to sustain a single breath. Earth's atmosphere, by contrast, is 21% oxygen, a composition that has allowed complex life to flourish for hundreds of millions of years. Mars does not simply lack the right air, it lacks air in any meaningful sense. But the composition is only part of the problem. The true danger lies in the pressure, or rather, the lack of it. On Earth, atmospheric pressure at sea level is measured at roughly 14.7 pounds per square inch. This pressure holds our bodies in equilibrium, keeps our blood liquid, allows our lungs to expand and contract with ease. On Mars, the atmospheric pressure is only 0.6% of Earth's. To put that in perspective, it is equivalent to standing at an altitude of 100,000 feet on Earth, higher than any jet flies, higher than weather balloons typically reach, at the very edge of what we consider space. At such pressures, the human body begins to fail in ways that are both immediate and catastrophic. Without a pressurized suit, a person exposed to the Martian atmosphere would experience what is known as ebulism. The low pressure causes the water in bodily fluids to vaporize. Saliva would boil on the tongue. Moisture in the lungs would turn to vapor. Blood would not boil immediately, protected as it is by the circulatory system. But within seconds, the tissues would begin to swell as dissolved gases came out of solution, like opening a bottle of carbonated water. Consciousness would be lost in 15 seconds. Death would follow within 1 to 2 minutes, not from the cold, not from suffocation alone, but from the violent depressurization of the body itself. In Antarctica, by contrast, we can step outside. We need insulation, certainly. We need protection from the wind and cold. But we do not need a pressurized shell between us and the environment. We can wear layers of fabric, not rigid engineering. We can remove a glove momentarily to adjust equipment. We can breathe deeply, feeling the sting of cold air in our nostrils, but knowing that each breath delivers oxygen to our bloodstream. The difference is not one of degree, it is one of kind. Antarctica is hostile, but it is still Earth. Mars is another world entirely. The engineering challenge this presents is staggering. On Mars, every structure must be a pressurized vessel, sealed against the near vacuum outside. Every habitat, every corridor, every living space must maintain Earth-like pressure constantly, without fail. A small puncture, a crack in a seal, a malfunction in a valve. These are not inconveniences. They are potential death sentences. The walls of Martian habitats must be thick enough to hold pressure, strong enough to resist micrometeor impacts, and flexible enough to withstand the thermal expansion and contraction caused by the planet's extreme temperature swings. We cannot simply build a structure and live inside it. We must build a container that holds Earth's atmosphere within it, a bubble of home suspended in an alien environment. Spacesuits become not occasional equipment, but constant companions. Every excursion outside, whether to repair equipment, conduct research, or explore the landscape, requires donning a full pressurized suit. These are not the lightweight garments worn by mountaineers in Antarctica. They are complex life support systems, each one a miniature spacecraft wrapped around a human body. They must regulate pressure, supply oxygen, remove carbon dioxide, manage temperature, and provide protection from radiation, all while allowing enough mobility to perform tasks. Putting on such a suit is not a quick process. It can take 30 minutes or more, with careful checks at each stage. Every outing becomes a carefully planned mission, not a spontaneous walk. The psychological implications are profound, though often overlooked in discussions of Martian colonization. To never breathe fresh air naturally, to never feel wind directly on your face, to know that a thin membrane of fabric and plastic is all that stands between you and instant death. This creates a constant underlying tension. In Antarctica, researchers describe the relief of stepping outside the base, even in brutal cold, just to experience the openness, the connection to the natural world. On Mars, there is no such release. The outdoors is not merely dangerous, it is fundamentally incompatible with human physiology. You can see the landscape through a helmet visor, you can walk upon it in your pressurized suit, but you can never truly be part of it. You are always separated, always enclosed, always aware that the environment beyond the suit is trying to kill you, not through malice, but through simple atmospheric physics. Some propose that future technology might alter this equation. Terraforming Mars, transforming its atmosphere over centuries or millennia into something breathable, is often discussed with optimism in scientific circles. The scale of such an endeavor, however, beggars imagination. It would require releasing vast quantities of greenhouse gases to warm the planet, melting the polar ice caps to release trapped carbon dioxide and water vapor, and somehow introducing or cultivating organisms capable of producing oxygen. Even with aggressive intervention, such a process might take thousands of years, and that assumes it is even possible that Mars has sufficient volatile materials locked in its crust and ice, and that we can prevent the solar wind from simply stripping away any atmosphere we create, as it did to Mars's original atmosphere billions of years ago. In the meantime, in the immediate future, the atmospheric problem remains absolute. Antarctica offers harsh conditions within a breathable envelope. Mars offers no such grace. Every single breath on Mars would need to be manufactured, filtered, and delivered through technology. Every moment outside a pressurized structure would require a spacesuit functioning flawlessly. There is no margin for error, no moment of casual interaction with the environment, no ability to simply exist as biological creatures under an open sky. This is not to say the challenge is insurmountable. Humans have proven remarkably adaptable, capable of living in submarines for months, in space stations for years, always within artificial atmospheres. But we must be honest, about what we are proposing. A settlement on Mars is not simply a difficult Antarctic base. It is an existence fundamentally mediated by technology, where the natural state of the environment is instantly lethal, and where the simple act of breathing requires constant mechanical intervention. In Antarctica, the air itself is familiar, welcoming, life-giving. On Mars, there's only the thin whisper of an alien atmosphere, beautiful perhaps in its desolation, but utterly indifferent to the presence of life. And in that difference lies one of the most fundamental reasons why even Antarctica, frozen and forbidding as it is, remains incomparably more habitable than the Red Planet. Cold is not a single experience. It is a spectrum, a gradient that ranges from uncomfortable to unsurvivable. Antarctica teaches us where human endurance ends. Mars reminds us that even that limit can be surpassed by orders of magnitude. Both worlds are frozen, hostile, and unforgiving. Yet the cold of Antarctica and the cold of Mars are not merely different in degree. They are different in nature, in behavior, in the very way they interact with matter and life itself. Antarctica holds the record for the coldest temperature ever measured on Earth. At Russia's Vostok station, deep in the heart of the continent's interior plateau, thermometers once plunged to -89.2 degrees Celsius, or -128.6 degrees Fahrenheit. This was not a momentary anomaly, but a genuine reading captured in July 1983, during the depth of Antarctic winter, when the sun never rises and darkness stretches across weeks. At such temperatures, exposed skin freezes in seconds. Breath crystallizes instantly into clouds of ice. Steel becomes brittle. Rubber shatters like glass. The cold at Vostok is not just felt, it is absolute, a physical force that transforms the world into something alien and unyielding. And yet, humans live there. Research stations dot the Antarctic landscape, their inhabitants surviving months in conditions that would seem impossible. They do this not because the cold is mild, but because it is predictable. Antarctica's temperatures, while extreme, follow patterns. Winter is severe, but summer arrives. Coastal regions can reach above freezing during the austral summer, allowing liquid water to flow briefly across the ice. Even at Vostok, temperatures can rise to a comparatively balmy -20 degrees Celsius in summer months. The cold in Antarctica is brutal, but it is not eternal. It breathes, it cycles, it allows for moments of reprieve. Mars offers no such mercy. The average surface temperature on Mars hovers around -63 degrees Celsius, colder than any inhabited place on Earth. But averages conceal extremes. At the Martian poles during winter, temperatures plunge to -125 degrees Celsius, colder than anything Antarctica has ever produced. At the equator, midday temperatures can briefly rise above freezing, reaching a fleeting 20 degrees Celsius for a few hours before plummeting back down at night. The difference between day and night on Mars is not gradual. It is violent, a thermal whiplash that can swing more than 100 degrees Celsius within a single rotation of the planet. This is where Mars reveals its true hostility. The thin Martian atmosphere, less than 1% the density of Earth's, provides almost no insulation. On Earth, our thick blanket of air traps heat, moderating temperature changes and distributing warmth across the planet. Even in Antarctica, the atmosphere cushions against the most extreme fluctuations. On Mars, there is no cushion. Heat radiates into space almost instantly. The surface loses warmth the moment the sun dips below the horizon. Without an atmosphere to hold it, thermal energy simply vanishes into the void. For humans, this creates challenges beyond mere survival. On Antarctica, thermal management is straightforward. Insulated habitats retain heat efficiently. Thick walls, multiple airlocks, and passive solar design keep interiors warm even when the world outside reaches Antarctic extremes. Heating systems are reliable because the environment, while cold, is stable. Engineers know what to expect. Materials behave predictably. Decades of experience have produced proven solutions, refined through trial and error across multiple research stations. On Mars, thermal management becomes exponentially more complex. A habitat must not only insulate against extreme cold, but also withstand rapid temperature swings. Materials expand and contract with each Martian day, stressing joints and seals. Electronics designed for Earth struggle in environments where temperatures fluctuate so dramatically. Batteries lose efficiency in the cold. Lubricants freeze. Even the regolith beneath a habitat conducts heat away relentlessly, pulling warmth into the frozen ground. Maintaining a stable internal temperature on Mars requires active heating systems that run continuously, consuming precious energy with no respite. There is another factor, subtle but significant. Antarctica's cold, while severe, exists within a context humans understand. We have evolved on Earth, adapted to its atmospheric pressure, its gravity, its thermal dynamics. Cold on Earth behaves in familiar ways. We know how ice forms, how frost accumulates, how materials respond. Our intuitions, shaped by millions of years of terrestrial existence, remain mostly reliable. On Mars, intuition fails. The thin atmosphere means convective heat loss behaves differently. Water ice sublimates directly into vapor without melting. Carbon dioxide freezes out of the air at the poles, forming seasonal ice caps of dry ice that vanish each spring. The rules of thermodynamics are the same, but their expression is alien, unfamiliar, and unforgiving to assumptions shaped by Earth. What makes this truly sobering is that humans have demonstrated remarkable ingenuity in adapting to Antarctic conditions. Modern Antarctic habitats are marvels of engineering, equipped with hydroponics labs, advanced life support systems, and even recreational facilities. Residents rotate through seasonal deployments, arriving in summer and departing before the worst of winter, or staying year-round as part of elite winter-over crews. They know that rescue, while difficult, is possible. Aircraft can reach most stations within days if conditions permit. Supply chains, though stretched thin, remain intact. The cold is extreme, but it is not insurmountable because humanity has had decades to learn its patterns, its dangers, its weaknesses. Mars offers none of this accumulated wisdom. Every solution must be theoretical until tested in situ. Every material must be validated against conditions no Earth-based laboratory can perfectly replicate. The difference between -89 degrees Celsius and -125 degrees Celsius is not merely numerical. It represents the difference between extraordinarily difficult and beyond current engineering limits for sustained habitation. And yet, Mars' temperature extremes, while more severe, are not uniformly worse than Antarctica's. The equatorial regions of Mars experience temperatures that, during midday, could theoretically allow liquid water to exist briefly on the surface, given sufficient atmospheric pressure. This is a tantalizing glimpse of habitability, a reminder that Mars, while hostile, is not uniformly lethal. Antarctica, despite its summer warmth, remains a continent buried under ice miles thick, inhospitable to unprotected life year-round. The comparison forces us to reconsider what cold truly means. It is not just a number on a thermometer. It is the interaction between temperature, atmosphere, materials, and life. Antarctica's cold is a knife, sharp and dangerous, but wielded in a familiar hand. Mars's cold is a shifting blade, unpredictable and alien, cutting in ways we are still learning to anticipate. Both demand respect. Both test the limits of human endurance. But only one exists within the protective embrace of Earth's atmosphere, that invisible shield that makes even the coldest places on our planet more habitable than the warmest moments on Mars. Water is the currency of survival. It is the foundation of every human civilization, the substance that defines the boundary between life and lifelessness. On Earth, we take its presence for granted, even in the most extreme environments. But what does water truly mean when we compare two frozen frontiers, Antarctica and Mars? The answer reveals not just a difference in quantity, but a fundamental shift in what it means to survive. Antarctica holds within its ice sheets approximately 70% of all the fresh water on Earth. Think about that for a moment. 7 out of every 10 drops of fresh water that exist on our planet are locked in the Antarctic ice. It is a frozen ocean suspended above bedrock, accumulated over millions of years, layer upon layer of snowfall compressed into glaciers that flow with the patience of geological time. This is not scarce water. This is abundance in its most extreme form, water so plentiful that the continent itself is defined by it. At research stations like McMurdo, the challenge is not finding water, but simply melting it. The process is almost absurdly straightforward. Ice is collected, brought inside, heated, and transformed into liquid. No complex chemistry, no elaborate filtration beyond standard safety protocols. The water beneath Antarctica's ice is some of the purest on Earth, untouched by industrial pollution, free from the contaminants that plague water sources on populated continents. A single glacier contains enough water to supply a research station for decades, perhaps centuries. The technology required is little more than heat and time. This abundance creates a psychological foundation that is easy to overlook. When you turn on a faucet at McMurdo Station, water flows. Perhaps not with the pressure of a city apartment, but it flows nonetheless. You can shower, you can wash dishes, you can, if needed, simply stand under warm water and let the cold of the continent drain from your body. This is not rationing. This is normalcy, preserved even at the bottom of the world. Mars offers a starkly different relationship with water. Water exists on Mars. This is not speculation, it is confirmed fact. Vast quantities of water ice lie buried beneath the Martian surface, trapped in permafrost layers that extend across much of the planet. The polar ice caps, visible even through modest telescopes, contain frozen water mixed with carbon dioxide. Seasonal flows detected on crater walls suggest that liquid water, or at least briny flows, may occasionally seep across the surface during warmer periods. Beneath the southern polar ice cap, radar has detected what appears to be a subglacial lake, a body of liquid water kept from freezing by pressure, salt content, and perhaps geothermal heat from Mars' interior. But knowing water exists and being able to use it are separated by challenges both technical and profound. Extracting water on Mars requires energy, substantial amounts of it. The Martian permafrost exists in a frozen state not because of temporary winter conditions, but because Mars itself is a frozen world. To melt this ice requires heating it from temperatures that can plunge to -100 degrees Fahrenheit or lower. The energy demands are considerable, especially when energy itself is scarce on a planet where solar panels produce only 43% of the power they would generate on Earth, and dust storms can block the sun entirely for weeks at a time. Even if we successfully extract water from Martian ice, the challenges have only begun. Mars is not a chemically neutral environment. The Martian soil is laden with perchlorates, highly oxidizing compounds that are toxic to humans and corrosive to equipment. These chemicals do not simply rest on the surface, they permeate the soil, and by extension, they contaminate the water ice trapped within it. Any water extracted from Martian sources must be extensively purified, not just filtered, but chemically treated to remove compounds that would sicken or kill anyone who drank them. Perchlorates are used on Earth in rocket fuel and fireworks precisely because of their reactive properties. On Mars, they exist naturally in concentrations that would render water unsafe without intensive processing. The irony is stark. Mars contains water, but that water cannot be trusted. Every liter must be questioned, tested, purified through processes that consume energy, time, and resources that are themselves precious beyond measure. Some scientists have proposed using Martian perchlorates as a resource, breaking them down to extract oxygen for breathing and fuel production. This is elegant in theory, but it adds layers of industrial complexity to what should be the simplest act of survival: getting a drink of water. On Mars, there is no moment when you simply melt ice and drink. Every drop is processed, every sip is engineered. The contrast becomes even clearer when we consider scale. McMurdo Station, during its summer peak, houses over 1,000 people. Its water systems, refined over decades of Antarctic operation, provide enough water for drinking, cooking, sanitation, and scientific research. The systems are robust, tested, and reliable. They represent proof of concept. Humans can thrive in a frozen environment when water, despite being frozen, is fundamentally accessible and safe. A Mars colony, even a small one, would face water challenges that dwarf those of Antarctica. Every system would need redundancy, backup purification, emergency reserves, rationing protocols for when equipment fails or energy runs low. The psychological weight of this scarcity cannot be understated. On Mars, you would know every single day exactly how much water you have, how much you are using, and how precariously balanced your survival truly is. Water rationing is not merely inconvenient, it is cognitively exhausting. Researchers who have studied isolated environments note that resource scarcity creates constant low-level stress. Every shower becomes a calculation. Every use of water for non-essential purposes, washing clothes, cleaning equipment, even the simple comfort of washing your face, becomes a decision weighted with consequence. In Antarctica, these concerns exist but are manageable. On Mars, they would define daily existence. There is something deeply human about the relationship we have with water. It is not just biological necessity, it is comfort. The sound of running water soothes us. The ability to wash is tied to dignity and psychological well-being. To be constantly aware of scarcity, to ration every drop, is to live in a state of perpetual caution that wears on the mind in ways that are difficult to quantify, but impossible to ignore. Antarctica teaches us that even in the most extreme cold, water can be abundant if the planet provides it. Mars teaches us the opposite. That even when water exists, a hostile chemistry, an energy-starved environment can render it nearly as remote as if it were absent entirely. Both worlds are cold. Both are frozen. But one offers a frozen ocean beneath your feet, waiting to be transformed with simple heat. The other offers ice locked in toxic soil, demanding industrial infrastructure just to make it safe enough to touch your lips. The difference is not one of degree. It is a difference of kind, a fundamental shift in what survival requires and what the human spirit must endure to obtain the most basic element of life. Above Antarctica, invisible forces shape the very fabric of survival. High in the atmosphere, Earth's magnetic field stretches thousands of miles into space, deflecting particles that would otherwise shred DNA with silent efficiency. This is not science fiction. This is the quiet miracle that makes life on Earth possible, a protection so fundamental that we have never lived without it. Until we consider Mars. As we stand on the frozen surface of Antarctica, cosmic radiation passes through the atmosphere above us, but it arrives weakened, filtered, reduced to levels our bodies can endure. The magnetosphere, generated by Earth's molten iron core spinning deep beneath our feet, acts as an invisible shield, bending and deflecting the solar wind that streams constantly from the sun. These charged particles, traveling at over 1 million miles per hour, could strip away our atmosphere entirely if not for this magnetic embrace. Earth has held this shield for billions of years, and Antarctica, despite its harsh reputation, rests comfortably beneath its protection. Mars once possessed such a field. Billions of years ago, when its core was still molten and churning, Mars too had a magnetosphere. But as the planet cooled, its core solidified, and the magnetic field collapsed. What remained was a world exposed, stripped bare to the radiation of space. The solar wind, no longer deflected, began eroding Mars's atmosphere particle by particle across eons. Today, Mars stands vulnerable, a planet without armor, facing the cosmos alone. The difference in radiation exposure between Antarctica and Mars is not incremental. It is existential. On Earth's surface, even in Antarctica, where the ozone layer thins seasonally, radiation levels remain within ranges that human biology has evolved to tolerate. Background radiation in Antarctica averages around 0.1 to 0.3 millisieverts per year from cosmic sources, slightly higher than at sea level due to the altitude and thinner atmosphere, but still well within safe limits. Our cells possess repair mechanisms honed over millions of years to handle this natural exposure. On Mars, the surface radiation is approximately 30 times higher than what we experience in Earth's safest zones. Annual exposure on the Martian surface reaches about 250 millisieverts, a dose that approaches the maximum recommended limit for nuclear workers on Earth for an entire career, received instead every single year. This is not a temporary spike from a solar flare. This is the constant, unrelenting background of Mars. Every moment spent on the surface accumulates damage at the cellular level, silently increasing cancer risk, degrading immune function, and potentially damaging the central nervous system in ways we are only beginning to understand. The radiation comes from two primary sources, each deadly in its own right. Solar radiation, the charged particles streaming from our sun, arrives at Mars with full intensity. Without a magnetic field to redirect these particles around the planet, they strike the surface directly. During solar storms, When the sun releases massive coronal ejections, radiation levels can spike to immediately dangerous levels. On Earth, our magnetosphere channels these particles toward the poles, creating the aurora borealis and australis, beautiful light shows that represent radiation we are not receiving. On Mars, there are no auroras to admire. There is only exposure. Even more insidious are galactic cosmic rays, high-energy particles originating from supernovae and stellar explosions across the galaxy. These particles travel at nearly the speed of light, carrying so much energy that they can pass through spacecraft hulls, habitat walls, and human tissue with ease. On Earth, our atmosphere acts as a thick blanket, absorbing these particles before they reach the surface. The magnetosphere provides a first line of defense, and the atmosphere, equivalent to about 30 feet of water in terms of shielding, provides the second. Mars has neither. Its atmosphere is so thin, less than 1% of Earth's, that it offers virtually no protection. Galactic cosmic rays strike the Martian surface unimpeded, day and night, without pause. The Antarctic ozone hole, discovered in the 1980s, caused global concern as an environmental crisis. This seasonal thinning of the ozone layer above Antarctica allows increased ultraviolet radiation to reach the surface, raising skin cancer risks and damaging marine ecosystems. Yet even at its worst, the ozone hole represents a temporary, partial reduction in one layer of Earth's multi-layered defense system. The magnetosphere still functions. The bulk of the atmosphere remains. Protective measures for Antarctic researchers include sunscreen, protective clothing, and limiting exposure during peak months. These are inconveniences, not existential threats. Mars has no ozone layer to thin. It has no atmospheric layers to speak of. The comparison is not between a damaged shield and an intact one, but between any shield at all and none. If the Antarctic ozone hole prompted international treaties and decades of environmental action, what does Mars's complete absence of protection say about the feasibility of surface habitation? This reality shapes every aspect of theoretical Mars colonization. On Antarctica, research stations are built on the surface. Walls made of insulated metal and wood are sufficient. Windows allow natural light to enter. Scientists can step outside in protective clothing and work for hours without concern for invisible radiation accumulating in their bones. The Antarctic. Summer offers 24-hour daylight, and researchers make full use of it, conducting fieldwork, maintaining equipment, and simply walking across the ice to preserve their mental health. On Mars, surface structures would offer minimal protection. To reduce radiation exposure to tolerable levels, habitats would need to be buried under several meters of Martian regolith, the loose rock and dust that covers the planet's surface. Some designs propose building into canyon walls or occupying lava tubes, natural underground tunnels formed by ancient volcanic activity. These solutions transform Mars colonization from a challenge of engineering to one of subterranean existence. Colonists would live underground, emerging only when necessary, their time on the surface measured and rationed like a precious resource that degrades with use. The long-term implications extend beyond cancer risk, though that alone would be profound. Studies on astronauts who have spent time aboard the International Space Station, protected by Earth's magnetosphere but above the atmosphere's shielding, show subtle cognitive changes and accelerated aging at the cellular level. Mars colonists would face far higher exposure over far longer periods. Genetic damage could accumulate across years, potentially affecting reproductive cells and raising questions about the viability of multi-generational settlement. Could children be safely conceived and carried to term in such an environment? Would they develop normally? These are not hypothetical concerns for a distant future. They are immediate questions that must be answered before the first permanent settlers depart. Interestingly, some scientists have proposed ambitious solutions. Artificial magnetospheres generated by superconducting magnets placed at Mars's L1 Lagrange point, or aerosol injection to thicken the atmosphere over centuries. These ideas, while theoretically possible, represent engineering projects of such scale and complexity that they dwarf anything humanity has attempted. They are not solutions for first-generation colonists, but perhaps for their great-great-grandchildren, if the colony survives long enough to implement them. Antarctica teaches us that humans can endure extraordinary cold, isolation, and darkness. But it also teaches us something more subtle, that the conditions we can endure are bounded by fundamental protections we often take for granted. We survive Antarctica not despite Earth's hostility, but because Earth, even at its harshest, remains a world designed for life. Mars is not. The radiation difference alone represents a chasm, not of degree, but of kind. It is the difference between a world that shields its inhabitants and one that has forgotten how. In Antarctica, survival depends on supply chains that stretch across oceans, but remain firmly tethered to Earth's living biosphere. On Mars, survival would require becoming something humanity has never been. Entirely self-sufficient on a sterile world. The challenge is not simply about growing food in harsh conditions. It is about creating life itself in a place where life has never existed. Antarctic research stations, despite their remoteness, are not truly isolated from Earth's abundance. Several times each year, supply ships push through the ice, carrying fresh produce, frozen goods, and the variety of sustenance that keeps human bodies and spirits nourished. During the Antarctic summer, planes land regularly at stations like McMurdo, delivering everything from vegetables to chocolate. Even at the South Pole Station, the most isolated permanently inhabited place on Earth, resupply missions arrive. The connection to civilization, though stretched thin across vast distances, remains unbroken. If a greenhouse fails, if crops wither, if systems malfunction, help arrives within weeks or months, not years. Some Antarctic stations have pushed the boundaries of self-sufficiency with remarkable success. Greenhouses constructed at McMurdo and the German Neumayer Station 3 produce fresh lettuce, tomatoes, cucumbers, and herbs. These are not massive agricultural operations, but supplements to a diet otherwise sustained by Earth's global food network. The greenhouses work because Antarctica, despite its hostility, still exists within Earth's protective embrace. Sunlight, though weak and seasonal, reaches the surface. The atmosphere, though frigid, contains oxygen. Water, frozen though it may be, is abundant and pure. With heat lamps, insulation, and careful management, plants grow. Slowly, yes, but they grow. Mars offers no such foundation. The Martian surface is not merely barren, it is toxic. The soil, which appears at first glance like reddish sand or clay, contains perchlorates, chemical compounds that are poisonous to most forms of life. Before a single seed could be planted, before any hope of agriculture could begin, the regolith would need to be processed, washed, and chemically treated to remove these contaminants. This is not simple gardening. It is industrial-scale soil remediation, requiring massive amounts of water, energy, and time. Every kilogram of Martian dirt would need to be transformed before it could sustain even the hardiest of Earth crops. Then comes the question of light. On Earth, even in Antarctica's winter darkness, the sun eventually returns, bathing the continent in continuous daylight during summer months. Mars receives roughly half the sunlight that Earth does, and what little reaches the surface is filtered through a thin, dusty atmosphere. Martian greenhouses would require artificial lighting for most crops, powered continuously by solar panels or nuclear reactors. The energy requirements are not modest. They are astronomical. To grow enough food for even a small crew would demand power systems on par with small towns, running without interruption, without failure, for years on end. Consider the timeline of failure on Mars. If a critical component breaks in an Antarctic greenhouse, a replacement part can arrive within days or weeks. If the same component fails on Mars, the resupply timeline is measured not in weeks, but in launch windows. Earth and Mars align favorably for travel only once every 26 months, and even then, the journey takes between 6 and 9 months. A part ordered today might not arrive for a year and a half. In that time, without fresh produce, the crew would survive on stored rations, watching their margin for error shrink with every passing soul. Yet the disparity goes deeper than logistics. Antarctica exists on the edge of life, but not beyond it. The Southern Ocean surrounding the continent teems with krill, fish, seals, and whales. Antarctic stations are permitted limited fishing, supplementing their diets with fresh seafood harvested from waters just beyond the ice. Microscopic life persists even in the harshest Antarctic environments. Algae blooms beneath the sea ice. Bacteria thrive in subglacial lakes. Lichens cling to rocks in the dry valleys. Life, though sparse, endures. This creates a subtle but profound psychological buffer. Humans in Antarctica are not alone in the biological sense. They remain part of Earth's living network, however tenuous the connection. Mars has no such network. It is a world of complete sterility. No fish swim beneath its ice. No microbes colonize its soil. No ecosystem exists to be harvested, studied, or simply observed. Every calorie consumed on Mars would need to be grown, synthesized, or imported from Earth. There is no foraging, no backup, no hidden reserves of life waiting to be discovered. The sterility is absolute. This reality elevates the importance of closed-loop life support systems to an existential necessity. On the International Space Station and in theoretical Mars habitats, these systems recycle water, regenerate oxygen from carbon dioxide, and compost waste to create fertilizer. They are marvels of engineering, delicate balances of chemistry and biology enclosed in metal shells. But they are also fragile. A single contamination, a single failure in the chain, and the entire system can collapse. Algae tanks can crash, bacterial cultures can die, pumps can clog, filters can foul. In space or on Mars, there is no opening a window for fresh air, no rain to cleanse the system, no natural cycles to restore balance. Antarctic stations, by contrast, do not require closed-loop perfection. Waste can be stored and eventually shipped back to civilization. Water can be melted from the endless ice. Air is exchanged freely with Earth's atmosphere. Even the act of opening a door, though unpleasant in the cold, is not lethal. The difference is one of forgiveness. Earth forgives mistakes. Mars does not. Some researchers propose that Martian agriculture could eventually utilize native resources. Subsurface ice could be melted for water. Atmospheric carbon dioxide could be harnessed for plant growth. Regolith, once treated, might be enriched with compost from human waste. These ideas are not fantasies, they are grounded in real science. Experiments on Earth have demonstrated that modified Martian soil simulants can support plant growth under controlled conditions. But the gap between laboratory success and full-scale agricultural sustainability is vast, measured not just in technology, but in redundancy, reliability, and time. There is also the question of variety. Antarctic researchers may eat monotonous meals for stretches, but resupply brings diversity, fresh fruit, spices, treats. The psychological impact of food variety is well documented in isolation studies. On Mars, the menu would be dictated entirely by what could be grown or stored. Potatoes, perhaps, lettuce, soybeans, rice. Nutritionally sufficient, but culturally and psychologically impoverished. The absence of Earth's agricultural richness would weigh on the mind as much as the body. Yet humanity has always adapted. We have learned to grow food in deserts, on floating gardens, in vertical farms within cities. The challenge of Martian agriculture is not impossible, but it is unprecedented. It requires transforming a dead world into a living one, not through terraforming over millennia, but through controlled environments sustained by human ingenuity and ceaseless effort. Antarctica feeds its inhabitants by extending Earth's reach across frozen seas. Mars would demand that its inhabitants become self-creators of sustenance, builders of oases in an infinite desert. The difference is not merely technical, it is philosophical. One is survival with support. The other is survival despite everything, a test of whether life can take root where none has existed before, sustained only by will, knowledge, and the fragile hope that the systems will hold long enough for the harvest to come. In Antarctica, if something goes catastrophically wrong, help is measured in hours or days. On Mars, help is measured in the time it takes planets to align. This is not merely an inconvenience, it is a fundamental transformation of what medical care means. Consider a researcher at the Amundsen-Scott South Pole Station who suffers acute appendicitis in the depths of winter. The situation is dire. Temperatures outside plunge to -80 degrees Fahrenheit. Darkness is absolute. No aircraft can safely land. Yet even in these extreme conditions, evacuation remains possible. In 2001, Dr. Ronald Shemensky performed his own biopsy and treated himself with antibiotics through the winter. When conditions allowed, he was evacuated. The window of rescue, though narrow, existed. Between the diagnosis and departure from Antarctica, roughly 9 months passed, but the possibility of evacuation was always present, always approaching. On Mars, that window does not exist at all. The journey to Mars takes, at minimum, 6 to 9 months using current technology. The return journey takes equally long. Launch windows occur only once every 26 months when Earth and Mars align favorably. This means that if a medical emergency occurs on Mars, the afflicted person has precisely 2 options: survive with whatever resources exist on Mars, or do not survive. There is no third choice, no emergency extraction, no medical airlift. The cosmos itself becomes the barrier, measured not in miles of ice, but in the inexorable mechanics of orbital dynamics. Telemedicine, which has proven revolutionary on Earth, becomes a fragile thread stretched across interplanetary distance. Communication between Earth and Mars travels at the speed of light, yet even light takes time to cross the void. Depending on the planet's positions, radio signals experience a delay of 4 to 24 minutes one way. This means a conversation with a doctor on Earth involves waiting 8 to 48 minutes between question and answer. Imagine performing emergency surgery with instructions that arrive half an hour after you ask for them. The surgeon's hands must move in real time, but their connection to expertise is frozen in the past. Every decision becomes isolated, every action irreversible. The nature of injury itself transforms in Martian conditions. A simple fall that might bruise on Earth could fracture bones weakened by months in reduced gravity. Mars's gravity is only 38% of Earth's, enough to keep you grounded, but not enough to maintain bone density and muscle mass as evolution designed them. Astronauts on the International Space Station lose approximately 1–2% of bone mass per month, despite rigorous exercise regimens. On Mars, similar degradation would occur, and there would be no quick return to Earth's healing embrace. A broken femur in Antarctica means pain, immobilization, and eventual evacuation. A broken femur on Mars means months of recovery in an environment where your skeleton is continuously weakening, where every step of rehabilitation fights against a gravitational field that is neither familiar nor sufficient. Surgery itself becomes an endeavor wrapped in unknowns. How does blood flow and pool in 0.38 g? How do anesthetics metabolize differently? If internal bleeding occurs, does the reduced gravity help or hinder the body's natural clotting mechanisms? These questions have no answers because no surgery has ever been performed in Martian gravity. We have theories, simulations, models built from parabolic flights and centrifuges, but theory and reality diverge most dramatically in moments of crisis. The first emergency surgery on Mars will be an experiment conducted with a human life as both subject and stake. Compounding every medical challenge is radiation. Mars has no magnetic field, no thick atmosphere to shield its surface from cosmic rays and solar particle events. Astronauts on Mars would receive roughly 0.67 millisieverts of radiation per day, accumulating to levels that increase cancer risk, potentially damage neural tissue, and compromise immune function. Now imagine performing surgery in this environment. Imagine an open surgical site exposed to radiation levels that would be unthinkable in any hospital on Earth. Imagine a patient recovering from surgery while their cells struggle to repair damage, not just from the procedure, but from the continuous bombardment of high-energy particles. Healing is not merely slower, it is contested. Then there is the question that touches the deepest human implications: pregnancy and childbirth. In Antarctica, despite the isolation and cold, pregnancy is theoretically possible, though strongly discouraged for practical reasons. Pregnant individuals can be evacuated if complications arise. But on Mars, pregnancy becomes an irreversible commitment to a biological process that has never occurred at 0.38 g under elevated radiation, in isolation from advanced neonatal care. We do not know if human conception can occur normally in Martian gravity. We do not know how fetal development would proceed. We do not know if birth itself would be viable. Mouse studies in simulated low gravity suggest developmental abnormalities. But mice are not humans, and simulation is not reality. The first child born on Mars, should such an event occur, would be entering existence under conditions no human has ever experienced, with risks no parent can fully comprehend. Psychological healthcare too faces unprecedented challenges. Antarctica's isolation can be psychologically taxing, yet researchers know their time is finite. They can count down to departure. They can hold in their minds the image of home waiting beyond the ice. On Mars, that certainty evaporates. The return is not guaranteed. It depends on technology that must function flawlessly, on launch windows that must be met, on resources that must be available. The psychological weight of this reality is difficult to quantify, but impossible to ignore. Some researchers have noted that astronauts experience what might be called the overview effect in reverse, a profound sense of Earth's fragility and distance that can be both beautiful and deeply unsettling. When psychological crisis occurs on Mars, therapy sessions happen across a time delay that prevents real-time dialogue. Psychiatric medications must be stockpiled for years, their efficacy in low gravity and high radiation unknown. If someone becomes a danger to themselves or others, there is no hospital to transfer them to. There is only the Martian base and the people within it. This leads to ethical questions that have no comfortable answers. If multiple people require life-saving care simultaneously, but resources can only save one, who decides? On Earth, medical triage follows established protocols, supported by the assumption that more resources can arrive. On Mars, resources are absolutely finite. The decisions made in medical emergencies become not just medical, but existential. They determine not only who survives, but what kind of society is being built in the red dust. The distance between Antarctica and Mars is not measured only in miles or months. It is measured in the presence or absence of rescue, in the possibility or impossibility of second chances. Antarctica tests human endurance, but Mars tests whether endurance alone is enough. In the frozen south, help is always approaching. On Mars, you become the only help available. And that distinction changes not just medicine, but what it means to be human in an indifferent universe. We turn away from the machinery and the metal and look inward, toward the one system we cannot upgrade or replace, the human mind. Antarctica and Mars are both far from home, both cold, both silent. But psychologically, they are separated by more than millions of miles. They are separated by the difference between a locked door and a sealed tomb. On Earth's southernmost continent, there is a season known simply as winter over. Once the last plane leaves and the sea ice closes in, no one comes and no one goes for months. The sun sets and does not return. Temperatures drop so low that even steel becomes brittle. Inside the stations, a smaller winter begins, inside the people who stay. Psychologists have a name for what happens there: winter over syndrome. It is not dramatic, not cinematic. It is slow, subtle. A creeping fog of lethargy, irritability, sleep disturbance, and emotional flattening. Some describe it as living life on mute. The days blend together, meals repeat. The same faces circle the same corridors. Even in a place filled with experts and carefully selected crews, cabin fever is not a joke, it is a data point. These stations are, in a sense, rehearsal rooms for space. We see how humans behave when cut off from the rest of the world. Minor annoyances become magnified. A shared kitchen can feel like contested territory. A misinterpreted comment can echo for weeks because there are no new people, no new places to dilute its impact. Group cliques form and dissolve, leaders emerge, falter or retreat. Some people thrive on the routine. Others quietly count the days. And yet, beneath all of this, there is a psychological safety net. The knowledge that Antarctica is still Earth. even as snow buries the station and winds scream outside at hurricane force. There is a thin, invisible thread tying each person to the rest of humanity. If something goes catastrophically wrong, rescue is not easy, but it is possible. A plane could be flown in when the weather breaks. A ship could fight through the ice. Helicopters, medical evacuations, international coordination, none of it quick, none of it trivial, but each of it real. Every person wintering over in Antarctica knows this. The way you know that somewhere beyond the horizon there are trees and rain and cities full of light. That knowledge is like an emergency exit sign in the back of your mind. Even if the door is locked for now, you know it exists. On Mars, that sign disappears. A colonist on Mars lives with a different kind of isolation. The door home is not blocked by weather or distance in the usual sense. It is blocked by physics, orbital alignments, propellant, technology that is still a sketch on a whiteboard. Going to Mars is not a season. It is a sentence, measured in years and possibly in lifetimes. Even the most optimistic mission plans speak in terms of multi-year stays. Launch windows open and close like celestial gates. You cannot simply decide to leave. There is no emergency airlift, no sudden evacuation. If you develop a serious medical or psychological crisis, there is only what you brought with you and the people who came alongside you. There is no hospital over the horizon, no neighbouring country, no Coast Guard, no search and rescue team flying through the storm. The knowledge of that permanence reshapes the mind. In Antarctica, people can say, when I get back to the forest, when I get back to the city, when I get back to my family. That expectation, that mental guarantee of return softens the edges of isolation. Time becomes a countdown. On Mars, the phrase shifts, if I go back. Or perhaps, they might go back, but I will not. For some, that might be exhilarating, a complete, irreversible commitment to a new life on another world. For others, it might press down like extra gravity. Every conflict, every bad day, every moment of doubt sits atop the knowledge that there is no quick exit. The station is not a remote outpost of Earth, it is the entirety of your world. Communication draws another invisible line between Antarctica and Mars. At the South Pole, you can send a message home, and the response can arrive in seconds. You can schedule a live video call. Hear your children laugh in real time. Share a meal over a laptop screen. Even at the bottom of the world, the internet crackles through the atmosphere, bouncing off satellites, keeping conversations alive. These connections are fragile but fast. A joke lands. A tear is seen as it falls. Voices overlap, interrupt, laugh together. It is not the same as being there, but it is close enough to quiet a certain kind of loneliness. On Mars, the speed of light stretches conversation into something else entirely. Depending on the alignment of the planets, a message may take between 4 and over 20 minutes to travel one way. Say something to someone you love, and nearly half an hour may pass before their reply begins its journey back. Real-time conversation dissolves. Interruptions are impossible. By the time you respond to someone's words, their mood may have changed. Their day has moved on. Imagine trying to comfort a friend through a delay like that, or argue, or apologize. Imagine a parenting moment in which your child on Earth wants to show you a drawing, and for them, you are always slightly late to the moment. You live permanently out of sync with everyone you left behind. Over weeks, months, years, this delay transforms relationships. Family and friends back on Earth age at the same pace, but their lives unfold as a series of recorded messages and staggered replies. Birthdays, holidays, milestones, they arrive as afterimages. Grief takes on a new shape when condolences are delayed by the finite speed of light. In Antarctica, isolation is physical. On Mars, it is temporal as well. Even when alone in an Antarctic station, you are still embedded in the sensory fabric of Earth. Step outside and your breath forms ice in the air. You feel the direction of the wind against your skin. The snow crunches under your boots. The sky, though dark, is familiar. Stars you know, constellations you recognize, the occasional shimmering curtain of auroras responding to the same sun that warms your home. Sometimes, wildlife appears at the margins of the station, penguins curious and unafraid, seals resting on the ice. Life, however sparse, still exists beyond the walls. The cry of a bird, the sound of the wind, the texture of ice, the scent of cold itself, these anchor the mind to something ancient and shared. You are far from civilization, but not from nature. On Mars, step outside and everything is alien. The sky is butterscotch, not blue. The sun is smaller, the light thinner. There is no sound of wind in trees, because there are no trees. Wind carries dust, but almost no force. There are no birds, no insects, no footsteps but your own. The silence is not the silence of a snowy field. It is the silence of a world where nothing else breathes. Inside the habitat, nature becomes a memory and a simulation. Screens show oceans. Hydroponic gardens hum with artificial light. Recorded birdsong may play in the background to soften the metallic echo of the walls. These solutions help, but they are approximations. The human brain evolved to read the world through patterns of natural variation. The rustle of leaves, the changing angle of sunlight, the chaos of waves. Mars offers rock, dust, and sky, static tableau on a geologic timescale. Antarctica teaches us that people can suffer even with nature just beyond the door. What then becomes of the mind when even that door opens only onto barren rock under a thinner sun? In the microcosm of an Antarctic station, we see the social dynamics of isolation play out on a manageable scale. These crews are small villages in a snow-covered world. Every interaction matters. Every disagreement is amplified. There is nowhere else to sit at lunch, nowhere else to sleep, nowhere else to go. Studies have documented how groups go through phases: initial excitement and cohesion, followed by tension, conflict, and eventually, if well managed, adaptation. The success of a mission often depends less on hardware and more on habits. Conflict resolution styles, communication norms, unspoken rules about privacy and shared spaces. Even trivial rituals, movie nights, themed dinners, pseudo-holidays, can stabilize morale. Antarctic missions have learned, sometimes the hard way, that selection and training are only the beginning. The way people give each other space, forgive small mistakes, and maintain a sense of humor becomes a survival system of its own. Leaders must walk a narrow line, too authoritarian, and resentment builds. Too hands-off, and cliques and grievances grow unchecked. Now stretch that small village across interplanetary space. On Mars, the social bubble is not just your winter. It might be most of your life. There is no rotation of fresh faces at the end of the season. No new crew flying in. The same voices, the same habits, the same interpersonal histories, day after day, year after year. In such a setting, even hope can become complicated. Talk of the next ship might inspire some and torment others. New arrivals could refresh the social ecosystem or destabilize it. The first serious conflict that cannot be escaped, that cannot be diffused by the knowledge that in a few months we'll all go home, will teach us what it truly means to live as a permanent off-world community. Beneath the logistics and psychology runs something deeper, something that Antarctica hints at but cannot fully reproduce: the existential weight of being on another planet. On the ice, step outside the station and you may feel very small. Above you, the Milky Way arcs across the sky with a clarity most humans never see. The universe feels immense and indifferent, but beneath your boots is still Earth, the only world known to harbour life. You're on the same sphere where oceans roar, where forests grow, where billions of people laugh and argue and make breakfast. You are an outlier, not an exile. On Mars, the existential question becomes louder. You are standing on a different chapter of the solar system's story. The constellations are skewed. Earth is not the ground beneath your feet. It is a star in the sky. For some, this might be the ultimate dream, a chance to be part of something unimaginably new, to help write the opening lines of a multiplanetary civilization. For others, the awareness could be quietly overwhelming. Every look out the window is a reminder: if anything truly goes wrong, you have crossed a distance that cannot easily be undone. In that sense, Antarctica is isolation with an exit strategy. It is a hard test, but the answers are still graded on Earth. Mars is not isolation. It is relocation. It asks a different question of the human mind. Not, can you endure being away for a while? But, can you truly let go of the idea that home is a place you can return to, rather than a memory you carry with you? As we compare these two extremes, the white continent and the red planet, we discover that habitability is not just air pressure, temperature, or radiation. It is also the ability of a human mind to wake up each day in a place that feels, in some deep way, survivable, not only to the body, but to the soul. Antarctica is not a friendly place. It is a continent of ice, wind, and darkness that can last for months. And yet, when a plane descends toward the white expanse of the South Pole, it is not arriving at a blank, alien void. It is landing on a world we have already learned to endure. On the ice, runways carved from compacted snow stretch across the frozen plain. Lights mark the edges. Pilots speak to control towers. Cargo is unloaded with forklifts. There are fuel depots and storage tanks, weather stations and radar, satellite dishes and fiber links reaching back to the rest of the planet. Antarctica is harsh, but it is wired into the same global network as New York, Tokyo, and Nairobi. We have been practicing survival here for more than a century. That time has not been measured only in years, but in failures, disasters, rescues, and slow, steady refinement. Every mishap has written another lesson into the ice, and every lesson has turned into a protocol, a checklist, a piece of infrastructure that quietly protects the next human who steps onto the frozen ground. On Mars, nothing like this exists. Not yet. There are no runways, no fuel depots, no spare parts warehouses, no hospitals, and no hangars filled with replacement equipment. There is only rock, dust, and thin, toxic air. Where Antarctica is an extreme outpost of Earth, Mars is an untouched frontier that must be built from zero, in a place where every mistake could be final. This is the difference between proven systems and theoretical solutions. In Antarctica, you can land. Today, multiple times a week in summer. There are long, groomed ice runways that handle large cargo planes. There are gravel and blue ice airstrips at research stations scattered across the continent. If the weather cooperates, you can evacuate a sick scientist from the South Pole, load them onto a plane, and deliver them to a hospital on another continent in a matter of hours or days. On Mars, the first landing is itself a major engineering gamble. No human has ever experienced the entry, descent, and landing profile required to bring a large, crude vehicle safely through Mars' thin atmosphere. Parachutes that worked on Earth have to be oversized and re-engineered. Retro rockets must fire at precisely the right moments. Supersonic flight must transition to subsonic hover, all over a landscape that offers no prepared surface, no control tower, and no second chances. In Antarctica, if a landing strip cracks or drifts with snow, we fix it with machines brought from Earth. Front-end loaders, graders, fuel trucks. We know what it means when a bearing fails or a hydraulic line fractures in the cold. There is a manual, there is an experienced mechanic, there is a crate that says spare parts. On Mars, the runway itself is theoretical, perhaps a clearing of dust, perhaps inflatable pads, perhaps vertical landing on exposed regolith. Each idea exists in simulations, blueprints, and testbeds. None has yet faced the talcum-fine dust that creeps into every joint, the temperature swings that stress every material, or the reduced gravity that changes how every piece of machinery behaves. Antarctica has a network. Mars has a hope. Across the white continent, dozens of research stations sit anchored to rock or ice. McMurdo, Amundsen Scott, Concordia, Vostok, Halley, Rothera. Some are small outposts, others are more like miniature villages. They're connected by satellite links that speak with constellations orbiting Earth. Those satellites route internet, phone calls, live video. A researcher in a storm can talk to their family. An engineer can consult with a manufacturer thousands of miles away. A doctor can show a scan to a specialist on another continent in real time. Power flows through buried cables. Diesel generators hum, backed up by wind turbines and solar arrays during the bright summer. Heated modules house workshops, labs, kitchens, sleeping quarters. If a critical piece of equipment breaks, chances are that somewhere on Earth, a similar device is running in a hospital, a factory, or another station. There is a supply chain, and the Antarctic bases are outposts along its farthest edges. On Mars, the first outpost will be the supply chain. Every bolt, every gasket, every circuit board will have to arrive on that world in advance, or be built from raw materials, dug and processed by machines we have not yet fully designed. Communication with Earth will not be instantaneous. Conversations will stretch across minutes of delay. Asking for help will feel less like a call and more like sending a message in a bottle that arrives long after the crisis has already unfolded. Our confidence in Mars technology rests on prototypes, on vacuum chambers, on simulation software and robotic missions that have survived for years on the surface. These are extraordinary achievements, but they occupy a different category than a system that has been used, broken, repaired, and iterated on by generations of people living with it in a place that routinely tries to kill them. The difference is not just technological, it is historical. When Scott and his team perished on the return journey from the South Pole in 1912, their bodies and journals were found only 11 miles from a supply depot. Their story is etched into Antarctic lore not as a romantic tragedy, but as a case study in planning, equipment choices, and the ruthless indifference of the environment. Shackleton's failed attempt to cross the continent and his miraculous rescue of his crew gave us more than an adventure tale. It gave us a manual on leadership in isolation and the limitations of early 20th century gear under stress. The men who hauled sledges on starvation rations through blizzards did not know that their suffering would one day translate into better clothing, improved shelter design, smarter logistics. Their mistakes, cotton instead of synthetic fibers, inadequate insulation, insufficient communications, became warning signs for those who followed. Today's Antarctic bases stand on a foundation of experience that was, in many cases, paid for with lives. Modular buildings are lifted on stilts so they can be raised above drifting snow. Some stations are built to be moved, sliding on skis across the ice as it shifts and fractures. Others are designed to be partially buried, using insulation and snow cover as a shield against the cold. Every choice is informed by what has failed before. Mars will demand a similar process of trial and error, but the errors will unfold at a distance of tens of millions of miles. The learning curve that cost lives on Antarctica's edge will, for Mars, play out with communications lag and perhaps without the possibility of a rescue. Engineering complexity behaves differently when the environment refuses to help. In Antarctica, every system is difficult, but the planet is on your side in small, crucial ways. The atmosphere provides pressure. Liquids behave as fluids instead of boiling into vapor in vacuum. Combustion engines can inhale oxygen from the air. Concrete cures. Metals expand and contract in ways we understand from countless other cold regions on Earth. On Mars, each of these assumptions fractures. The air is too thin and carbon dioxide rich to breathe, but also too faint to carry much heat. Any habitat must provide pressure artificially, or bodies and systems will fail. Solvents evaporate or freeze in unfamiliar ways. Dust storms charge the air with electricity, potentially interfering with electronics and coating solar panels. Temperature swings can crack materials designed for more stable environments. Every additional layer of engineering is a new possible failure point. Airlocks must hold. Pressure vessels must remain intact for years. Life support systems must recycle air, water, and waste almost perfectly, because there is no resupply ship dropping in with backup tanks, just in case. What is a nuisance in Antarctica? A fuel spill, a broken pump, a torn cable, can be met with a repair team, a spare, and, if needed, a new delivery next season. On Mars, even the simplest maintenance task is magnified by context. Imagine a broken valve in a Martian greenhouse. On Earth, a technician pulls a replacement from storage or orders another overnight. In Antarctica, they wait for the next flight or improvise a patch that holds until it arrives. On Mars, there is no warehouse just over the horizon. There is only what the crew brought, what they can salvage, and what they can manufacture from the local environment. Manufacturing on Mars is not swapping out a part. It is recreating, at planetary scale, the industrial backbone Earth has assembled over centuries. Mining, refining, fabrication, quality control. To produce a single high-precision component might require an entire chain of upstream tools and processes. Each of those tools must itself arrive intact, be maintained, and be fed with raw material. Each maintenance step spawns another branch of required expertise. Energy is where this compounding complexity becomes most obvious. Antarctic stations rely on logistics. Diesel arrives in bulk via ship and overland traverse. Fuel is stored in tanks that are refilled every season. Solar panels capture the high, clear summer sun. Some bases experiment with wind power, spun by the relentless katabatic winds pouring down from the plateau. If a generator fails, another can be shipped in. If an entire energy system proves unreliable, it can be redesigned, replaced, or upgraded with technology perfected elsewhere on Earth. Mars has no such safety net. There are no tankers docking at orbital ports to refuel the colony. Every watt must come from local generation. Solar arrays stretched across the dusty plains, nuclear reactors buried for safety, perhaps later wind turbines brushing the thin air, or geothermal systems sipping heat from under the crust. Energy storage must bridge not just a night, but potentially long dust storms that darken the sky for weeks. A Martian outpost must be, from day one, almost completely energy independent, not just for comfort, but for survival. Heating, air circulation, water purification, food production, communications, transport, every breath and every bite is an energy equation. Batteries and fuel cells, flywheels and chemical stores, all built or shipped, all finite, all subject to wear and decay. In Antarctica, if an experiment consumes more power than expected, a station can power down some labs or bring in additional generators in the next supply season. On Mars, miscalculating energy demand could mean shutting down entire systems to keep the essentials alive. The margin for error is far narrower, and every solution must work the first time in conditions no human has yet felt on their skin. Yet, this is not an argument that Mars is impossible. It is a reminder that we've sent rovers there and people live in Antarctica are not equivalent statements. The ice continent is a test bed we can reach, monitor, and resupply. It is a harsh teacher, but one that sits at the edge of a world overflowing with backup plans. Mars is a teacher we can only approach once we have done our homework. And in a quiet, surprising way, Antarctica has been one of the classrooms. From early wooden huts to modern modular stations, we have learned how to build structures that can be assembled quickly in the cold, anchored to unstable ground, and maintained by small crews over long winters. We have studied how people cope with constant darkness and isolation, how equipment fails when lubricants thicken and plastics become brittle, how to design clothing that balances mobility and protection. We have tested remote medicine, psychological support, telepresence, and autonomy. These lessons, written in the white silence of the South, are already shaping the concepts. For Martian bases, pressurized tunnels, buried habitats, redundant life support loops, distributed power grids. The difference is that in Antarctica, if something critical goes wrong, the entire planet is a phone call away. On Mars, the planet is still there, but as a tiny, distant light in the sky. Antarctica shows us what it looks like when a hostile environment is woven into our technological web. Mars asks us to imagine building that web from nothing at the end of a very long, very thin thread. When we compare habitability, we are not just comparing air and temperature. We are comparing how much of our civilization we can reliably bring with us, and how much of it we must reinvent under a different sun. On Earth's southernmost continent, the systems that keep people alive have been tested, broken, and made better across generations. On Mars, those systems still live on whiteboards, in code, and in prototypes. Between those designs and a breathing human standing in the red dust lies a distance not just of millions of miles, but of experience. We have weighed the air, measured the cold, counted the calories, and traced the long, fragile thread that would have to connect any Martian settlement back to Earth. By almost every practical metric, Antarctica wins. It has air pressure. It has a magnetosphere overhead and an ozone layer filtering the sun. It has liquid water, reluctant, seasonal, and salty, but real. It has a hospital flight away, not a planet away. And yet, when we look up at the night sky, most of us do not dream of building domes on Antarctica. We dream of Mars. On paper, this makes little sense. If the question is, where can humans most easily live outside our cities? The answer is obvious. We should be covering Antarctica with insulated research towns, not sketching colonies on a world where the air itself is poison. But the human story has never been written only on paper. It is written in questions, in risks, and in the stubborn feeling that some places call to us even when they make no promises of comfort. So we step back from the engineering spreadsheets and the survival checklists and ask a different question. If Mars is so hostile, why is it still so compelling? Part of the answer lies in something Antarctica cannot offer. Another world. Mars is not just a location. It is a chapter in the solar system's history, bound in rust and dust. The rocks there remember a time when rivers carved valleys, when lakes pooled in craters, when the sky was thicker and perhaps bluer. Mars froze in the middle of its story. By going there, we are not just surviving. We are reading a lost book of planetary evolution. Every core drilled into Martian regolith, every layer of sediment exposed on a crater wall, is a record of climate change on a scale our species has never witnessed. On Earth, erosion and plate tectonics erase and rewrite the past. Continents drift, mountains rise and grind back into the sea. But Mars is quieter. It keeps its scars. Just as the asteroid belt is an unfinished sentence in the formation of planets, Mars is an unfinished Earth. Not quite habitable, not quite dead. Hovering on the threshold, it offers us a mirror held at a strange angle, showing what might have been, and perhaps what might yet be for other worlds. This is the first layer of Mars's value. Scientifically, it is priceless. From the question of ancient life, to the chemistry of its soil, to the delicate dance of its thin atmosphere, Mars is a natural experiment that has been running for billions of years. Antarctica, for all its extremity, is still an outpost of Earth. Martian dust is not just cold, it is alien. The ice there is not just frozen water, it is a library of solar winds and cosmic radiation going back eons. When we dig into Antarctic ice cores, we learn about our planet. When we drill into Martian ice, we touch the history of the entire inner solar system. Then there is the argument that echoes more loudly each year. Mars as a backup. The second planet idea is simple to state and difficult to fully believe. If something catastrophic happened to Earth, an asteroid, a runaway climate spiral, a global war, perhaps a self-sustaining settlement on Mars could preserve our species, or at least our knowledge. A seed vault of humanity planted in red soil. It is a romantic image, a small dome glowing on a cold desert world, keeping the flame of consciousness alive while Earth heals or falls silent. But when we examine this argument closely, its limitations become clear. A Martian city would begin as more fragile than any village in Antarctica. Every breath, every sip of water, every calorie of food would depend on technologies working perfectly, endlessly, in a place where repair is slow and replacement parts are months away. For many decades, maybe centuries, any settlement on Mars would rely on Earth as its life support system. Launch windows, cargo ships, spare filters, software updates, medicine. A backup that needs its original to survive is not a true backup. It is a satellite, an outpost, an experiment, and yet, even here, the second planet argument does not die. It evolves. Because the very effort to make Mars less fragile would force us to master skills that also protect Earth. Closed-loop life support, hyper-efficient agriculture, robust recycling, materials that last for decades under harsh conditions. If you can grow a forest inside a dome on Mars, you can probably feed a city in the middle of a heatwave on Earth. The backup planet might never stand alone the way we imagine, but the technologies developed for it could make our primary world more resilient. The dream of Mars, in other words, pushes us to become better custodians of Earth. Antarctica has already done this once. It taught us that cooperation is not optional at the edges of survival. It showed nations that scientific data can be shared even when politics cannot. It revealed how delicate our climate really is, as trapped air bubbles told the story of carbon and ice responding to each other like partners in a slow planetary dance. It warned us of sea level rise long before waves began to nibble at our coasts. Mars, if we go there not just with flags but with patience, can teach us something different. How to build a civilization when everything we take for granted, air, water, warmth, sunlight, is in short supply. Imagine standing inside the first real Martian greenhouse. Outside, the wind is whisper thin. Temperatures swing from cold to killing cold. Radiation hums invisibly through the dust. Inside, a breath of humidity fogs your faceplate. Rows of plants drink light from LED arrays that mimic a sun 50 million miles away. Every molecule is counted. Every gram of waste is reused. This is not just survival. It's a new way of thinking about living. Antarctica has given us a rehearsal for isolation and logistics in the cold. Mars would be a rehearsal for something harder to name: intentional civilization. A society that knows, from the first shovel of regolith, that everything it does must be sustainable, or it will die. And yet, for all of this, there is the simple, stubborn fact of the timeline. You can buy a ticket to Antarctica today. You could, in theory, stand on the ice within weeks. There are runways, research stations, protocols, weather satellites, emergency plans. The continent is harsh, but logistically, it is near. It lives within the same atmospheric envelope as your home. Mars is not near. A fast transfer takes 6 to 9 months, and you have to wait for the orbits to align just to begin. There are no rescue helicopters warming up on a pad in Patagonia. There is no Coast Guard, no medevac, no emergency supply ship that can arrive before the next launch window. For at least the next several decades, Mars will remain a destination for instruments, then small crews, then perhaps a precarious outpost. Antarctica, by contrast, could be scaled up now. If humanity wanted to, we could build large, semi-permanent habitats on the ice within a single human lifetime, using technologies we already trust. From a strict cost-benefit perspective, this is an easy equation. If you want to learn how humans live in extreme cold, if you want to practice building pressurized habitats and closed-loop systems, if you want to stress test the human psyche in long polar nights, Antarctica offers a laboratory you can reach in hours, not years. But cost-benefit is not the only equation we use to live our lives. There is a quieter term in the human calculation, one that is hard to express in numbers: curiosity. Curiosity is the force that made us cross oceans when we already had land. It is the reason we dive into caves that offer no gold, only darkness. It is why we built telescopes to study stars that will never warm us. Antarctica satisfies our curiosity about Earth. Mars speaks to a deeper itch. What does it mean to be a species that can leave its cradle? The explorer's spirit is not rational in the way budgets are rational. It accepts risk that no cost-benefit analysis would ever justify. It drove ships into uncharted waters and climbers onto lethal slopes. Sometimes it ended in tragedy, but over time, it also expanded our sense of home, from valleys to continents to the entire planet. Mars is the next expansion of that word, home. Comparing habitability between Mars and Antarctica might feel, to some, like an attempt to scold the dream, to say, see, it's too hard, stay here. But the comparison does something very different. It adds texture. It reminds us that Mars is not a magic escape hatch, not an easy solution to Earth's problems. It is a harsh teacher, not a forgiving refuge. Recognizing that Antarctica is more habitable does not dim Mars's importance. It sharpens it. Because when we admit how difficult Mars truly is, something interesting happens. The people who are still willing to go, to research, to design, to dedicate their lives to red deserts and thin skies, they are not doing it because it's easy, or because they believe Mars will quickly replace Earth. They are doing it because there is something there worth learning, even at enormous cost. That in itself is a measure of value. And perhaps, before we reach too far, there is a middle path, learning to make Antarctica thrive as a training ground for Mars. Imagine vast modular habitats on the polar plateau, built to Mars-like standards. The air inside is fully recycled. The food is grown in stacked hydroponic farms. Waste is not managed, it is transformed, every atom accounted for. Communications are delayed artificially to mimic the light speed lag between Earth and Mars. Crews rotate in and out on multi-month cycles, seasons blurring into one another under a pale, low sun. Outside, the temperature sinks to levels busy city dwellers never have to consider. Inside, life depends on a web of systems designed as if no rescue were possible. Because one day, on another planet, that will be true. In this frozen rehearsal, we would discover weaknesses in our designs before they become fatal. We would learn how human minds bend and stretch under true isolation, but with the safety net of Earth still within reach. Antarctica becomes not a consolation prize, but a proving ground. A place where we practice not only how to survive Mars, but how to deserve it. Because underneath the romance and the risk, there is a quiet moral question. Should a species that cannot keep one planet healthy be allowed to expand to another? There is no cosmic referee to answer this for us. But how we treat the most fragile places on Earth, the poles, the oceans, the high deserts, may be the closest thing we have to a qualifying exam. If we can build sustainable, respectful, resilient communities at the edge of Antarctica's ice, we show ourselves that the dream of Mars is not just escapism. It is an extension of our growing responsibility, not an attempt to run from it. In the end, the cost-benefit analysis of Mars is not just about fuel and radiation, distance and delta V. It is about what kind of species we choose to be. Antarctica tells us what it takes to persist on the harshest parts of our own world. Mars asks us what we are willing to become to step onto another. Between them stretches not just miles and budgets, but a question that will define the coming centuries. Will we treat other worlds as expendable frontiers or as rare, solemn invitations? Mars, for all its thin air and bitter cold, remains compelling because it is both a challenge and a mirror. It forces us to confront our limits and our ambitions at the same time. And as we weigh ice against dust, storms of snow against storms of solar particles, a strange realization emerges. The place that is hardest to reach may be exactly where we learn the most about who we are. As our comparison between the red planet and the white continent draws to a close, we find ourselves back where all true space journeys begin and end, with Earth. We set out asking a simple question: why is even Antarctica, one of the harshest places on our world, more habitable than Mars? The answer, after exploring air, water, temperature, radiation, food, medicine, and the human mind, is unexpectedly profound. On Mars, every breath is a technical achievement. Every sip of water is an engineering triumph. Every step outside is a calculated risk. On Antarctica, those same actions are difficult, dangerous, and demanding, but they are still possible within the framework of a living planet. The air is thin and frigid, but breathable. The water is frozen, but abundant. The radiation is real, but filtered by a magnetic field and an atmosphere that work tirelessly, silently, without us ever needing to ask. Mars demands a full life support system before the first human heartbeat can safely echo across its surface. Antarctica, for all its brutality, still plugs into Earth's operating system by default. Gravity holds you at a familiar weight. The sky still scatters blue. The sun still rises and sets in a rhythm life already understands. If your heater fails, you can still inhale and shout for help. On Mars, a single failure is not an inconvenience. It is a timeline measured in minutes. This is the quiet, humbling revelation at the heart of planetary habitability. Earth cheats in our favor, everywhere, all the time. Our atmosphere is not just a mix of gases, it is a planetary contract signed over billions of years, promising liquid oceans, stable climates, most of the time, and the gentle pressure that allows our blood to flow without boiling or freezing. Our magnetic field is not merely a scientific curiosity. It is an invisible fortress deflecting solar storms that would sterilize unprotected worlds. When we say that even Antarctica is more habitable than Mars, we are not insulting Mars, we are acknowledging how exceptional Earth is. The most extreme place on our planet is still nested inside a biosphere so exquisitely tuned that it makes space stations look like prototypes and Mars habitats like sketches in the margins of a cosmic blueprint. This comparison matters for our future in space because it reshapes the story we tell about exploration. Colonizing Mars is not just moving to a colder, drier place. It is attempting to build a pocket of Earth in a world that has never known oceans, forests, or breathable skies. It is choosing to live inside a machine, one that must work perfectly, indefinitely, in an environment that does not care if we succeed. And yet, that challenge is exactly why Mars still calls to us. Understanding how good we have it here doesn't cancel the dream of going there. Instead, it clarifies what that dream really requires. It means that before we imagine cities under crimson sunsets, we must master closed-loop life support, radiation shielding, sustainable food systems, and robust mental health strategies for people who can never simply go outside without a suit and a plan. The comparison with Antarctica also offers a sobering benchmark. If we struggle to maintain year-round presence on a remote, cold, but fundamentally Earth-like continent, with full access to global supply chains, emergency evacuations, and decades of polar experience, then we gain a more honest sense of what Mars will demand. Not to discourage the attempt, but to respect it. To approach it with the same care and humility we would bring to stepping out onto thin ice over deep, dark water. As we look up at the night sky, it becomes clear that the real lesson of planetary habitability is not that Mars is hopeless, but that life is rare and fragile, and that living worlds are miracles of balance. Earth is not just our starting point. It is our reference model, our teacher, and our proof that under the right conditions, matter can become aware enough to wonder why the sky is red on one world and blue on another. So as you drift towards sleep, listening to these thoughts about frozen deserts and distant plains, consider this. Every breath you take right now is supported by a planet-sized life support system you did not have to build, maintain, or even notice. Oceans recycle your water. Forests and plankton refresh your air. The planet spins, the field deflects, the climate flows. You exist inside the most advanced habitat humanity will ever know, whether you live in a city of millions or on a quiet street under a single dim lamp. One day, we may walk under an alien sky and see Earth as a pale star rising over Martian hills. When that happens, the people living there will owe their survival not only to rockets and reactors, but to the lessons we learned from places like Antarctica, frontiers where Earth's embrace grows thin, but never fully disappears. If you'd like to keep travelling through ideas like this with us, across planets, ice sheets, and the quiet corners of the cosmos, feel free to support the channel by liking this video, subscribing, and turning on notifications so you don't miss future journeys. It helps more than you might think. Tell us in the comments where you're listening from tonight. What part of this remarkably habitable world you call home? And if you want to go a step further, you can join our YouTube membership to help support the channel and the work that goes into these videos. It's completely optional, but deeply appreciated. For now, as the stars wheel quietly overhead and the world turns beneath you, remember, among all the planets we know, you are already on the most extraordinary one.